about Mr. Somerville and right, and how he is my parents' neighbor. We cleaned up just because we didn't want you to go home and say, Sarah, Kelsey's classroom is a mess and her kids are crazy, right? We didn't want that. So they're going to be on their best behavior, and they've been super excited. They actually had to finish their project just so that they could come into this. That's their buy-in.
All right.
So they've been working very, very, very hard.
Great. Well, I hope it's worth it. Hello everyone, I'm Dr. Somerville, and I'm a scientist. I love to do demonstrations and teach people about science because I think science is really cool. So the first thing I'm going to show you is a tool that I like to use in the lab. I also use it in my kitchen. It's called a magnetic stirrer. And inside, I'm just going to reach in here. Basically, the idea is inside of this Teflon overwrap, there's a magnet, okay? So this is a magnet wrapped in plastic. And inside of this box, there's a magnet on top of a motor. So when I turn this motor on, the magnets will make each other move, and it mixes for me. So you can see that it causes the magnet to move. And so it's going to mix this stuff up. This is really useful for dissolving stuff like in the kitchen or whatever. So this is going to take a minute for this stuff to dissolve. And meanwhile, I'm going to show you something related to something that Kelsey mentioned that she was, Ms. Armitage was mentioned that she was trying to explain to you. It's an interesting concept, but it's kind of difficult to get across. And that's the idea of a colloidal solution or colloidal suspension and how it differs from a true solution. So I'm going to put this aside for a minute. Put this one on. Okay. Did you get a laser pointer?
Carmen. We don't. Jesse, go get Miss Boots' Dr. Seuss one, and we can see if that one will work. Yeah, ask her for her Dr. Seuss one.
Okay. So I'm going to shine this light here through this water, and you'll notice that it's just like you can see the light shines through it, right? Yeah. Now, there happen to be some things floating around in this water because the water is not pure, but if it was really pure water, you couldn't see anything in there. And what's in here is like bits of dust. Can you see those moving around?
Yeah.
Okay. So what I'm going to do now is I'm going to put some sugar in here. And you'll see how useful the magnetic stirrer is, like in the kitchen. Okay. So, you ever tried to dissolve, super, thank you. Have you ever tried to dissolve sugar into like a cold drink and with a spoon? You know, it takes forever. So I keep one of these in the kitchen so that I can dissolve stuff without having to bother with it like that. So the water, the sugar's pretty much gone into solution. Almost. Enough for this demonstration. So I'm going to shine this light through this again, and you'll be able to see that it hasn't really changed. It looks about the same, right? I'll try it with the laser. Wow, that laser is pretty weak.
Yeah.
I thought I came with my laser pointer, but I didn't. That's okay. This white light will do the trick fine. So what's happened here is the sugar is actually dissolved in solution, and it's completely dissolved down to its individual molecules of sugar. Okay? So if this is left for a long time, it's just going to stay a solution of sugar, and it's not going to change. Now I'm going to add something that's essentially extremely finely divided sand. It's silica Sand is made of something called silica, mostly, and this is super finely divided silica. So I'll put just a tiny bit in here, just a tiny bit, and mix it around. And it doesn't really change the appearance of the solution all that much. But now when I shine a light through it, you can see the light beam. Is that something you guys can see from there?
Yeah.
When this was first discovered, it was discovered like in the 1800s by a guy named Kendall. And so this is called the Kendall effect. So the thing about a colloidal solution is that even though these particles, which are causing this light to reflect, are not individual molecules, the particles are so small that this will never settle. So let me explain why that is. So if you have like a beaker with some water in it, or something like that, and there's a molecule of sugar in it, okay? That molecule is going to sort of bounce around in a random pattern. It won't be pulled down by gravity because it's so small that the water molecules kind of get in its way. So it's going to randomly bounce around and stuff like that, okay? It's getting hot in this jacket. And you may have heard that light can be thought of either as a particle or a wave. Has anyone ever heard that? Okay. So the thing about a colloidal solution is the particles are big. They're big enough. They're big enough to actually see, like with an electron microscope. You can actually see them. But they're not big enough to be pulled down by gravity without being bumped around by all the water molecules around it. So these colloidal solutions will never settle. Whereas if you were to put something like sand in the water and give it a little time, of course it'll settle down. But colloidal solutions, which is one thing that I think your teacher was trying to explain to you, will never settle. But they will reflect light. Because when the light is traveling through the solution, it travels kind of like a wave, like this. And if it encounters a particle that's kind of the same size as the light, it'll bump into it and it'll go boing, and it'll get like bounced off the particle. So instead of going like just straight through like it does in this case, it bumps into particles and some of it goes straight through, but some of it gets bounced off toward in all directions. And that's why you can see it, because some of it's reflected toward you. I know you. Miss Noga, right?
Yeah.
Yeah.
I saw your code. You worked at Girl.
Yeah, that's right. Your dad is my boss.
Yeah.
Yeah.
You're dead.
Good thing I told him I was going to be here this morning. Huh? So anyway, sorry about that. You did a fun job. Kind of surprised. So molecules are much smaller than a colloidal particle. So a light wave coming along won't bounce off of it like it will off of an actual particle. So that's what's happening here. These particles are about the same size as light waves. So they interact and they bounce off. So you can make this kind of solution yourself at home using cornstarch. And there are a lot of colloids that we eat every day, like Jell-O and stuff like that, are colloidal solutions. So it's really fun to do this experiment with a laser beam, because you can, for example, put a mirror over here and bounce the light around inside the colloidal solution, you can actually see the light move around and how it responds to, for example, a mirror or a lens. So, does anyone have any questions about that?
You guys are gonna have to know that stuff in next unit, because you guys are learning about the electromagnetic spectrum, you're learning about refraction and all of that. So this stuff you will definitely remember when we start our next unit. Emily, did you have a question?
Yeah. It's about that little thing that's on the everything. Like, what are the two little dots there?
Oh, this one?
Uh-huh.
So I'm getting ready for the next demonstration, and those two little dots are small amounts of this stuff, which is called methyl red, which is something that's going to change color depending on what kind of condition it's in. And the reason I wanted to show you this next demonstration is to show you like how the solution moves in this stir, which is kind of fun. It's just taking a while to dissolve. So I'm going to let that dissolve for a little while I move on to the next thing. So one of the things that Ms. Armentrout mentioned to me is the concept of volume and thinking about volume. So how do you
There's an
erase?
eraser in the middle of the board. Is that one?
That's pretty cool. Oh, I see. It's where the little dot goes. Okay. That's clever. Alrighty. Okay, so if somebody says volume, what do you think of? Like, anybody? You?
Size,
Okay. Yeah?
the amount of space.
The amount of space, very good, okay. Yeah,
Sometimes I think of it like in sound.
like a sound? Oh, volume, right, as in how high volume. Okay, I'm talking about physical volume, but that's a good one, yeah, good answer. Yeah,
The amount of space something takes up.
uh-huh, very good, okay.
Like a container and the space inside it.
Uh-huh, right, okay. So, one thing that sometimes people kind of get stuck on is thinking of volume as a formula, but it sounds like you guys have a concept of volume that's a little more advanced, and that's what we're going to talk about. So, like for a cube, the volume, of course, is equal to the length times the depth times the height. That's what you know, right? Length times depth times height. And for a circle, does anyone know that?
Height sounds
It's a little more advanced. It's 4/3 pi r cubed.
What?
Where
Oh,
this is the radius, or r. So what I'm trying to point out is sometimes with a perfect shape like this, it's easy to calculate the volume. And you run into this kind of thing in the real world. You kind of know, you know how big something is or something. Yes?
Would it be area or that volume? Would it be like diameter times radius or is that area?
Area is pi r cubed. So volume is like three-dimensional, whereas area is two-dimensional. It's like, you know, like a flat plane. So it takes a third dimension. That's where this r cubed comes from. It takes a third dimension to make the volume happen. So what happens if you run up? But in the real world also, not only do you encounter perfect shapes like this, you also encounter irregular shapes like this. So you can think of a way to measure the volume of this. Yeah? That's a good one. That's a good one. So he's saying, like, take something like this and put it inside and see how much the water rises. That's good. That gives you the outside volume. Yeah?
I see
Right, so I'm going to determine the volume of this by using this. It's called a graduated cylinder. So on the side, it has graduations in milliliters, and it goes up to 500. So if I don't manage to spill most of it, turns out this one is about 480, and on the bottle it says 473. At least that's how much they put in it. I had it filled all the way up to the top. So another way to do it is to fill something like this up to 500, for example. Fill it up all the way to the top, then pour it out of here into the bottle. Oops. And measure what's left. And for that, they have graduations on the side that go down. They go from 0 to 500, in addition to 0 to 500 on this side. So anyway, it sounds like, you know, some of you have a real concept of what volume is, but it's not just an equation. Yeah.
How would you find the volume of something that couldn't be filled, like a solid, that isn't hollow? How would you find the volume of that you couldn't pour water?
Your classmate's suggestion of, you could do it by, for example, you could fill this thing all the way up, and then have the water tipped, have it tipped over like this, and then immerse this thing. It would cause the water to overflow into something else, and then you could measure the water that overflowed, and that way you would get the volume of the outside of it, which is pretty close to the volume of the inside of it in this case. So it is possible to mathematically determine something as complicated as this, but it's just a lot easier to do it using a practical measurement. Alrighty, looks like this thing's ready. So any more questions about volume? No? Okay.
We have one.
Oh yeah? Okay.
Is it another way to measure like a solid instant pot is like to break it up into, if it's like that bottle, you could break it up into like different shapes and then
That's exactly how you would do it. Yeah, you would sort of model this as spheres, and then, you know, spheres and cylinders and stuff like that, and try to put it together. That's how you do it. And a lot of times it's not necessary to know the exact volume. Just you know sort of ballpark. And in that case, it would be possible to use formulas like that without too much hassle. You can get pretty close. Alrighty. Okay. So